Hello, everybody. My name is Miao. I'm very happy to present our work performance analysis of generalized product codes with irregular degree distribution. I'm a PhD student at Karlsruhe Institute of Technology, and this is joint work with my colleagues and my supervisor. I will start with a brief overview of this work. So we start with the background. So the starting point is the product code, which you can see here, is a two-dimensional array. And they are arranged in this way such that every row and column are code words of the component codes. And in this case, in the example here, we choose both component code to be a BCH code, but you can also choose any other component code. And the advantage is that if we arrange the bits in this way, we can use iterative decoding in a very low complexity manner because of the low complexity decoding algorithm of the component code and also because of the low amount of message passing. This is why they are widely used in high throughput systems. Okay, and then we consider generalized product codes, which we are allowed to use different optimization techniques such as spatial coupling or mixed component codes. And here we have an example here as the staircase code. You can see that if we look at these first two blocks, we can say that we make them this way such that every row is again like the product code, a code word of the component code. And then we can attach another column here such that every column here is again code word, and we can do this so on and so forth, and then we have an infinite amount of bits that we transmit, and this is a spatially coupled product code. And conventionally, we only consider the regular case where every bit is protected by exactly two component codes, as in this product code or in the staircase code. And then recently we have some works that are devoted to look at the irregular case where we allow a bit to be protected by arbitrary amount of component codes. As long as the number is bigger than or equal to 2, then we have iterative decoding. And you can actually think that by optimizing such structure, we should be able to further improve the performance. And then because we don't know too much about how to optimize these codes, then it is valuable to look at some theoretical performance analysis such that we can avoid just using monocolor simulations to optimize the codes. And this is the goal of this work. I will just briefly walk you through the way of derivation, how we can achieve this analysis in the end. So we look at product codes as an example, but you can easily extend this for general case later. So we look at this PC. We want to model them as a generalized LDPC codes in the following way. So this is a 2D array, which has n squared bits. Then every row and column is a component code. And in this case, we can draw them this way, that we have all the variable nodes and then all the check nodes. And then how do we connect the bits how do we connect the nodes? We can see that for the first row, we can do this. We see that every bit is connected to its corresponding column, and also all of them are connected to C1. And then for the second row as well, and all the way to the last row, then we have built the telegraph. And then we look at the binary erasure channel, which we will perform our analysis. And so in this case, Vn is the same as in the usual LDPC codes where we have repetition code. And the important thing is that they are recovered if any of its connected check node recovers it. Then we also have a component code, which is the check nodes. They are able to correct up to T erasures. That is to say, if we have less than equal to T erasures, we can recover the code word perfectly. Otherwise, we just return the input and declare failure. And it's important to know that this is intrinsic message passing, meaning that if we consider the incoming edge of from one variable node to a check node, we also consider the input when calculating the output for the same edge, because we are counting how many erasures this check node is connected to. Okay, so this requires a different way of analysis from LTPC codes, which we are giving in the next couple of minutes. So we want to additionally introduce something called a hypergraph, which is needed if we consider this irregular case. So what is a hypergraph? Here we have a graph and a hypergraph. A graph is just nodes and we have edges which connects them. But in a hypergraph, we allow edges, we change the edge to hyper edge, which is a subset of vertices. So you can think that every edge is a subset of cardinality 2. But in hyper edge, we allow the cardinality of an arbitrary amount. And in this case, here we just use the circle, which we also used for variable node to denote a hyper edge for the reason that you will understand in a couple of minutes. And then we can see that hypergraph is just a generalization of graph. And hyper edge, the edge is no longer just a simple edge, but a subset of the vertices. Then we can consider the telegraph of a GPC that we just obtained earlier, which here we can allow arbitrary connections, not just regular. Then we use the CNs as vertices, and the VNs, we consider them as hyper edge. So this VN, for example, V1 will give us a subset C1, C2, and C4. Then we say this is a hyper edge in the hypergraph. And the CNs are just vertices. Okay, this change of perspective is very important for the analysis. And then we consider random graphs, which is, you can imagine them this way, that you have a set of vertices, you name them, and from 1 to n, then you place them there, and you first, we don't consider the edge. Now, consider this model. We have a probability P, which is the probability of an edge occurring, and every edge occurs independently with probability P. Then you can imagine that when P is 0, the graph is completely empty because there's no edge. And when probability P is 1, then the graph is fully connected. And the important thing is actually the transition from non-connected to fully connected is not smoothly growing, but actually when P is close to some threshold or some critical region, then the random graph has a very sharp transition called phase transition from not connected to fully connected. So this transition happens very fast, which is similar as our decoding behavior where we have the waterfall. And in our case, we don't only consider the case of fully connected, we are more specifically interested at the graph property such that they are changing from decodable to not decodable. And this will be our approach. We want to model the erasure patterns as random graphs, and then we determine this phase transition behavior. And we want to mention that this is the extension of the work by Jäkel et al. The difference is that they only consider the regular degree, VN degree 2 case, where they don't consider hypergraph, but just graphs. And in our case, we want to allow arbitrary degree distribution, which is the contribution of this work. Okay, now we want to encode the deterministic structure of the GPC before we can model the erasure patterns. Why is that? Because we realize that for generalized product codes, their structure is very regular in the sense that comparing to LTPC code, where you have each particular bits can have arbitrary connection. So every bit is essentially different. But in a generalized product code, for example, the product code that we saw earlier, then every row and every column, this connection is very similar. And we can do this by grouping those similar rows and columns, check nodes, into different positions. Then we see that we can later model the erasure pattern in a pretty simple way. And this is why now we partition them into 3 positions. We look at this example here, which is the 3D product codes. It has check nodes along axis X, Y, and Z. And then we can say this is position 1, position 2, position 3. So here like this. And then we also want to define the type of the edge, which is determined by the multiset. So multiset is just a set, but we allow repeated elements. And so the type of edge is determined by the multiset containing the positions it connects to. And this gives us an inhomogeneous graph, which just simply means that every edge is associated with a type. And then in this example here, every hyperedge is of type 1, 2, and 3, as you can see, because every bit is connected to X, Y, and Z checks. And then we want to define something called connection tensors, which looks a bit complicated at the beginning, but this is the idea. It is a set of tensors, so A2, A3, all the way to R max. And this R denotes the degree of VM, meaning that we want to look at the subgraph consisting only degree R Vn and represent this connection by this AR here. How? In the way that we record the number of such degree R hyperedge per check node between different positions. This is the example. We have, for the 3D product code, we have A2 and A3 because R max is 3. And then A2 is 0 because we don't have any degree 2 connection. And A3, for example, A1, 2, 3 is 2 because we look at the connection between position 1, 2, and 3, and we realize that there will be 2 variable nodes that connects the 3 positions, and this is essentially the same for other positions. And then we look at we can finally define the hypergraph a random hypergraph that we are going to use by looking at ensembles of residual graph. So what is a residual graph? You can imagine them this way. We have a tenor graph, which we have explained how to explain earlier. So we have this tenor graph, then you can imagine every hyperedge as some sort of socket. Then we have a channel which introduces the randomness by the way that only some of the bits are erased. And this is the erasure of the bits are independent with probability P. And in a residual graph, we want to only look at the bits that are erased. So we only keep the ones that are erased. So it's a bit counterintuitive. That's why they are called residual graph. Then you can imagine if residual graph is empty, then we have succeeded with decoding. There's no erasure anymore. And then we can put this residual graph, then we look at all the possible residual graphs as a result of the randomness of the channel. Then this is essentially a random graph model, random hypergraph model, okay? Then we want to look at the transition behavior. So one thing that we realized that we can only do asymptotic analysis, meaning that we have to let the number of vertices in the random graph go to infinity. Then we want to scale the finite random graph that we defined earlier to infinity in the following way. And we can look at one particular check node at position I. Then in this example, we consider 2 types of hyperedges connecting to. Then we realize that if we let the number of total possible hyperedge go to infinity, then we know every hyperedge occurs independently with probability P, a binomial distribution. Then the amount of hyperedge that occurs is exactly Poisson distributed. And we need to calculate the mean value of the Poisson distribution. And here we just simply let them to be P times this division here. And the important thing is that we want to keep the fraction of number of possible this type hyperedge divided by the total number of position I vertices. We want to keep this fraction as the entry of the connection tensor. That is to say, we are scaling this hypergraph, random hypergraph to infinity, but we are keeping the average check node degree. Okay, so one last thing to obtain the overall distribution is we realize that we can add those two distributions together, because in Poisson distribution it has a merging property. Then is the total amount of hyperedges just Poisson distributed, and we simply can add the mean value together. Okay, now we have calculated the distribution of amount of hyperedge per check node, and essentially we can do it for any check node. And then we can also form a branching tree of depth L, which is the number of decoding iteration. Then we can start peeling from the bottom to up, as I said before. If we can finally, by the decoding rule, able to empty this residual graph, then we are able to decode. So we want to calculate the average property. That is, we start from the bottom, then we know this yellow area, we know the distribution of hyperedge because we have calculated earlier. Then we see that the check node is able to correct up to T erasures. That is to say, if this Poisson distribution takes value more than T, more than or equal to T, because there's another one going up, then this vertex, this check node will survive, and we will not be able to peel it, and everything else will be peeled. And then we can go one step higher, and we look at this hyperedge between those two check nodes in the neighboring level, and we realize if we want to keep this hyperedge, we would need to have both of its connected check node to survive. Otherwise, it's corrected, because a bit is corrected if any of its check node corrects it. Okay, so this is why there's a product. Then we can go one step higher and see that for this check node, the fraction of its offspring hyperedge survives is PS, which is the surviving probability of this we calculated. And we also know that for Poisson distribution, if we just now let the average number to be reduced to a fraction, we can also say that this is still a Poisson distribution, just with a reduced mean. And in our case, it's PS times lambda, which was the original lambda mean value. Okay, so this would be the framework of the derivation. And then we can put everything together and write it into an equation. And here we have xi is the probability of a bit at the position I that is not recovered after L decoding iteration. And we can put this into an iterative form, that here we can calculate xi L plus 1 using the connection tensor and the value of xi from the last iteration. And then the use of connection tensor makes this equation very compact, and it's also easy to calculate because you would not really store this high dimensional tensor. You actually just need to define the non-zero entries, which is actually pretty sparse for codes. Then we denote this as a decoding evolution to be different from density evolution. And then we want to look at the how accurate we can predict. And we can look at the 3D product codes, which we showed as example, but there we use a very small one. Here we use a more realistic number. So this BCH code, and we want to use it for binary symmetrical channel, which is a bit more used in a practical case. And if we assume no miscorrection, then we see that our analysis on the binary erasure channel can perfectly be applied. Then you can see that if you look at the solid and dashed curves, so for different iterations L, they always closely agree, which means our derivation works quite well. So this brought me to the end of my presentation. We have derived a random graph-based decoding analysis of GPCs, and the theoretical predictions align well with Monte Carlo simulations, and this gives us a new tool in designing GPCs. And we also have other results in the paper. For example, we proposed a novel extended staircase codes. Then we look at the impact of different degree distribution using decoding evolution. And we also look at the different decoding schedules, which are also quite important for generalized product codes, because we don't actually use a flooding schedule, because if you look at, for example, product codes, you are always decoding rows and columns alternatively, so it's not we're not decoding them at the same time, so which means the decoding schedule is also quite important. And then this would be all of my presentation. If you are interested, you can look into the paper, and if you have questions, feel free to contact us or leave a comment below. Thank you very much for your attention.